Today we're going to take a look at where does the derivation for the lateral area of a cone come from. Now we know from class that we were given the surface area of a cone comes from two terms. We have pi rs plus the second term of pi r squared. Now the second term, that's probably pretty obvious. It's just the area of a circle, and that's going to be the base of our cone. But the more interesting question is, where does this pi rs come from for the lateral or the side area of this cone? And that's what we're going to dig into today. Okay, just before we go too far, just want to show you what the net or the flattened picture of this cone looks like. A couple things I want to point out to you. If we look at this curved surface here along the bottom, just realize that that is simply the circumference of this circle below. And we've talked about this variable before, this s. That is the slant height. You also see it over here in the picture. Those are a couple main variables that we're going to deal with. Okay, before we dig into the direct problem, I would like to step back and just take a quick look at integral calculus. We won't talk about this probably for a few years yet, but it does apply here. And really all integral calculus allows us to do is to find the area under a curve that may not be a straight line. Now this is a little bit of an oversimplification, but let's say we were looking at this first graph and we want to estimate the area. Well, we could divide it into rectangular boxes. You know, I could slice it up like this into boxes, and that might give us an estimation of the area. In fact, for the height of the boxes, we could even take the midpoint if we wanted to get a little bit better estimate. However, let's take a look at the graph number 2 over here. If we wanted to get even a better estimate, one of the techniques we use in calculus is to use thinner and thinner, or I guess more narrow boxes to estimate the area under the curve. And the thinner these boxes are to estimate the area, the better our estimate would be. In fact, we can make these boxes infinitely thin in area. So a little bit of a look at integral calculus. We're going to see how this is going to apply down below in very simple terms. Okay, back to our problem at hand. Okay, first of all, I've drawn the net here of just the lateral surface area. I decided to split this lateral surface area into little triangles. The first thing I did was just draw these black lines, just split it up, and you'll see it kind of makes a pyramid type shape as it pinches towards the top. And then I said, you know, using the same sort of approach we had before, our estimate will get better and better if we make these divisions even smaller. So I split it again with these red lines. Assume that they're all evenly spaced out. Okay. And just a quick reminder too of the dimensions of what we're working with here. Right, this is our slant height here. And along the bottom we'd have circumference, which is pi d, which also can be written as 2 pi r, just double the diameter. Okay, all along the bottom here. Okay, how are we going to estimate this area? Let me just label a few things here for us. I'm going to say, let's call this first box number 1, this second box number 2 as I skip one. I'm going to call this A, and I'm going to call this B. Okay, bear with me here. So I'm going to highlight this here in yellow, yellow. I'm going to grab every second one, yellow, yellow, and yellow. that's going to correspond to this figure on the left as these little triangles, yellow, 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 yellow. Let's go back now and grab the ones that we missed. Okay, so here's A, here's B, etc., etc., etc. And so if I was to label them up here, this would be, that's going to be 1, that's going to be 2. Okay, A and B, we're going to flip them upside down so they fit in there really nicely. So this is going to be A, and this is going to be B. And let me color those in the green color. So that is, let me get the highlighter here. Yeah, so that would be this green here, that green there, green, green. So we've essentially taken this cone and put all the numbers along the bottom here to flatten them out here, and all the second letters along the top here to flatten this out. And essentially we've taken this shape, rearranged all those triangular slices, flipping every second one, to make a rectangular shape that we can easily figure out what its dimensions are. Because remember, this is simply S here. Okay, this is the one that gets interesting here. So we've taken every second slice. So it was C equals pi d equals 2 pi r, but I've only taken every second one, right? Like I've taken along the bottom this one, this one, this one. So it's only 1/2 of 2 pi r. If I do that, that is simply pi r. So take this value here, and up we go. Write that in. There is pi r. And so this whole thing of a rectangle, area, equals length times width, is simply pi r s. If you remember, that was the surface area of the lateral part of the cone. And so hopefully you found that helpful just to figure out how that formula is derived. I know some of you will enjoy seeing the proofs. Others may not be quite there yet, but I hope you maybe like to first look at this, how this was derived. That's it for now. Bye, and we'll see you later.